All right, so let's write it down. The topic here, was it page 5? Yeah, we're in page 5. So the topic will be surface area of revolution. So in your book, it's section 8.2. I'm going to start with the surface area of a circular cylinder, but I'm going to put it on the side. Okay, so let's look at a circular cylinder. And let's say this is a circular cylinder. Think about the drum, right? Like a 55-gallon drum, but without the bottom or the top. So it's lying on the side. I'm debating whether to write on the side. No, keep it upright. I think you are clever enough to make the visual adjustment. So this is the cylinder, circular cylinder, and I'm looking for the surface area. Again, this is open, bottom, open, top. The radius is R, and the height is H. Now, if I cut it open, then it will be a big rectangular. It's like think about taking a page of paper and roll it to make a cylinder. So you open it up. Now the length of the paper will be the circumference, right? And the circumference will be 2 pi r, and the height will be the same height. Now, if I want to take the differential approach to the area of the surface. What I mean by that, I'm going to take a very, very small cut right here. Okay, so when I flatten the envelope, this will be what I'm doing. Okay, and I say so small that this is DH. Okay, or let me write it here. This much is DH. In other words, infinitesimally infinitesimal part of the height. Okay, now what is the surface area of this infinitesimally narrow strip of envelope? Well, the length is still going to be 2 pi r, so I'm going to say that the element, infinitesimal part of the area, dA, will be simply 2 pi r times dH, and therefore the overall area will be the integral, let's say from 0 to something, of 2 pi r dH, or simply 2 pi rh, which we know to be the surface area of the cylinder. So this will be the approach to find irregular shape. Okay, so now think about the following example. Using this idea, let's look at a curve that we're going to rotate about the x-axis. Okay, so let's say we have a curve like so. Okay, so this is the curve y equal f of x. And we're going to take the piece of the curve from x equal a to x equal b, like so. And now we're going to rotate it about the x-axis, like so. All right? So what happened now, we have a body of a solid of revolution, and we can figure out its surface area. Okay, after revolving it, we have something like that, almost a bell shape in this case. Okay, and we're interested to know what is the surface area. We know what is the volume. So what I'll do, I'm going to take the differential approach one more time. I'm going to take this little piece right there, and this piece is a piece of the curve. Okay, so I'm going to use the arc length function and say this will be simply ds from before. Remember the ds function. And now I'm going to cut this very thin strip of material like so, and the height is ds. The radius is going to be r, or y in this case, right? So r equals y, and I'm going to say that dA, the small, infinitely small element of the area, is 2 pi r times ds, or in this case it will be 2 pi y ds. And what is ds? Well, again, ds is what we did before, is the arc length function. So we know it's the square root of 1 plus dy dx squared. So we can say that this equals in turn to 2 pi y times the square root of 1 plus dy dx squared, like so. And of course, ds is also, we have dx here. So this is the differential approach. We've done this before. And now we're going to say that the surface area will be the integral from a to b, because we go from a to b of dA, like so. Well, you tell me, are you integrated in the x, the x's or the y's? In this case, it's the x. We're going to talk about rotation, about the y-axis, and of course, the variable of integration in this case will be the y. This is very similar in a way to what we did when we did volume of solid of revolution. But again, you look at what is the infinitely small element, or what is the differential? ds in this case is in the direction of x. All right, so here we come with the function. The function will be, so this is the theorem, the surface area of revolution will be, and I can take the 2 pi out, or we can leave it actually for the time being. It will be the integral from a to b of 2 pi y times the square root of 1 plus dy dx squared dx, like so. Okay, so this is the approach. Let me go ahead and start with the first example, and then I'll give you some, if time permit, I'll give you some variation. So here goes. The first example, the curve y equals the square root of 4 minus x squared, and x goes from, let's say, negative 1 to positive 1, is an arc over the circle. Do you know what circle we're talking about? X squared plus y squared equals 4. You knew that, but you were too shy to speak to me. Find the area, find the surface area of revolution about the x-axis. Okay? So what is the deal in solving it? Let's find dy dx first, okay? Because I'm looking here, I need 1 plus dy dx squared. So if y equals the square root of 4 minus x squared, then dy dx equals to what? This is 4 minus x squared to the power of 1/2, right? So it will be 1/2 times 4 minus x squared to the power of negative 1/2, or we divide by the square root. But then we need to take the derivative of negative x squared, so it will be negative 2x. So we end up having, let's see if I have room here, we end up writing a negative x over the square root of 4 minus x squared. I do have. Okay. The next thing I need to do is find what is 1 plus dy dx squared. Well, that would be 1 plus negative x over the square root of 4 minus x squared. So it will be 1 plus x squared over 4 minus x squared. Okay, and if I make a common denominator here, 4 minus x squared, then I have 4 minus x squared plus x squared. I simply have 4. Okay? And now we are pretty much ready to continue with our integration. So, A, the area, will be the integral from negative 1 to 1 of 2 pi y. Remember, y is the square root of 4 minus x squared times the square root of 1 plus dy dx squared. So the square root times the square root of 4, should have written 2 here, over 4 minus x squared. You can see that these two cancel each other. Square root of 4 is 2. So at the end, we end up having something really easy in the integral from negative 1 to 1 of 2 pi times 2 or 4 pi dx. And of course, the result will be 4 pi x evaluated from negative 1 to 1, and this will be 8 pi. Okay, couple of comments before we move on, or before we call it a day. Okay, first, if instead of y equal f of x, if the curve is given by x equal g of y, as before, then what we have for the area, and again, y, let's see on CD, as we did before, y goes from c to d, then a would be the integral from c to d of 2 pi y. We are still rotating about the x-axis, so the radius is still going to be y, but the arc length is now in terms of dy, dx dy. So it will be the square root of 1 plus dx dy squared. And what is the variable of integration? Dy. Okay? Again, this is when we rotate about the x-axis. Okay. Speaking on rotation, this will be the last comment here, comment 2, and this is in general when we are looking at rotation. Okay, so we'll write the following: rotation about or rotating about. And then we have the surface area. The arc length will be ds in any event. So if we rotate about the x-axis we saw before, then the surface area will be the integral of 2 pi y ds. ds can be either y equal f of x or x equal f of y, right? But if we rotate about the y-axis, then the surface area will be a integral. If you rotate about the y-axis, the radius is x, so the change will be 2 pi x ds. Okay? When ds is expressed in terms of either y equal f of x or x equals g of y, which we saw. Okay, I'm going to stop here. This is the time to stop anyway.